In this, the second video of my mini-series on mastering vectors, we're going to unpack the complex topic of tension, and we'll do this within the context of a question from an A-level physics paper that's on pulleys.
We have some kind of pulley system with a big weight, or a relatively big weight of 35 newtons, and then that's connected through this wire around a pulley wheel and around another wheel. So that means that all along this line the tension is the same all the way because it's one piece of wire. Right, and we're asked to find what is the tension in C. Take out a triangle and try and draw this out. We have the tension in C like this, so we could call that tension C, and then we have a tension like this from the top wire M to P, so this is point P, and then we have a same tension in this wire that is kind of going from M to the bottom point.
But surely that's wrong. Well, actually, no, it isn't. Imagine a rope that's under tension. It's been stretched. Take a part of that rope somewhere in the middle. That little section feels forces to the left and to the right, equal and opposite. They're both tension forces. When dealing with tension in questions, you always have to think about what is the tension acting on. Well, in our question, the tension is acting on the pulley wheel in the middle, so it's downwards. But at the end where the rope is fixed on that little rectangle bit, the tension is upwards. That's why we've put our vector for tension down.
Remember, we're interested in the forces that are acting on that pulley wheel. That's why we can draw them like this. And in both cases, we've got an angle of 55. Now, the tension in the cable C is only acting along the X direction. Therefore, we need to take the tension that's in these cables and look for the X components. We're going to have something like, let's call it T. It goes down through the wheel and is connected to 35 newtons. So that means that this will be 35 newtons. Now, at the same time, we could break that force down into two components, X component and a Y component. And the Y, let's call it TY, has no effect because, you guessed it, it's at 90 degrees to TC. So we need to get the tension X. We know this angle is 55. We now find ourselves with a vector here, which is the hypotenuse, and an adjacent. So therefore Tx is going to be the size of our hypotenuse, T, times the cosine of 55. So that's the component of one of these tensions acting to the right. But of course we've got two of them. So we could say that Tc equals two lots of tension in the X direction. We can then go on to say that Tc equals two lots of 35 times the cosine of 55. And when you work that lot out, you get that Tc is equal to approximately 40 newtons. Now I have to say, I actually think that's a bit harder, that one, because it's confusing to think about. Why is it that these two forces are going in kind of different directions in the string?
Now that you've conquered tension, hopefully, it's time for us to move on to that perennial favourite of the exam boards, forces on a slope.